All right, folks, let's start. This is Dr. Yuzo. This is ECE 341 Power System class. Can you guys hear me? How about the screen as well?
Yep.
Any trouble? Good, good, good. Thank you, Ken. All right. So again, as usual, we take a look at our Gantt chart, see where we at. September 30th. September 30th, right here. Here. So September 30th, we're here. And obviously today we're gonna do the one review. And also I think we're gonna have time to talk a little bit about the quiz, Okay, so this is the plan for today. Before all of those, let's continue our symmetrical component examples. Okay, we have one more examples to do. But before that, even before that, this is the second example, I believe. The given is the symmetrical component. Symmetrical component. What does it mean by symmetrical component? You need to be very clear on this concept. Okay. Here, first of all, Neil is asking per unit example. I'm not forgetting it. So either today or the next lecture, because we still have one more lecture before the midterm one. Okay, so we're not forgetting that. Okay, definitely we will be there. Okay, we'll be there. All right, come back to here. So symmetrical components means, first of all, if voltage, we are talking about voltage, we are talking about phase voltage. Phase voltage and the phase A voltage, positive, negative, zero sequence components. So 3. Okay. So inside of these symmetrical components, everything is phase A component, just for different sequence. Okay. So there are two concepts. One is phase, different phase. We have 3 phase, A through C. And then we have parallel 3 sequence components. 3 sequence. They are positive sequence, negative sequence, and 0 sequence. So what? 3 by 3 up to 9 components. Does this make sense? 3 phase by 3 sequences. Okay, so 3 by 3 up to 9 components. Okay, this is concept need to be very, very clear. Okay, 9 components up to. All right, so going back to this example 2, we are given the symmetrical components, phase A positive, negative, and 0 sequence. And of course, be careful. Okay, be careful. Yeah, this is a VA plus minus 0. Yeah, VA plus minus 0. Okay. So based on this, we have these equations. And if you prefer the metrics, that's fine too. But be careful. Be careful. Which is which? Which is which? And then this is a result. And also we plot these result into the phasor diagram. Okay. And if this is clear, then we keep doing some more questions about this example too. Okay. And now let me give you some time. You guys just exercise to plot one symmetrical component to one graph. Into one graph. Second, plot what? Plot different components. Plot phase A 0 sequence, 0 sequence component. Phase B positive sequence, and phase C negative sequence. These 3 things into one graph, or say into another graph. Let's see if these are clear. All right, give you guys sort of 3 to 5 minutes. Try to plot these. Okay. Once again, symmetrical components should be in your notes already. So let's plot these into obviously two phasor diagrams, phasor graphs. Go ahead. Go ahead. 3 to 5 minutes. So let's see the solution for the first graph. First graph, the symmetrical component. By the way, can you guys hear me? Yes. Oh, good. Let's go on. So symmetrical components, as we see, is over here, right? Here. So 1.8, 0.6. So once again, we need to begin with the vector, or say the phasor with the maximum, the biggest magnitude, so 1. So one angle of 30 degrees. So just be careful. 130 degrees is about here, right? It's about here. I think this is fair 30 degree, and to make it long enough, because this is the biggest one. You don't want to have it too short, right? This is the VA, what is it? Plus, right? VA plus. Negative 30 degree is here. Negative 30 degree for VA minus, and the length is 0.8. 0.8 is, I would say, about here. This length is fair enough, I think. VA minus, and then 90 degree 0.6. 0.6 is even shorter here. 6, so it's about here. Right. This is a VA0. Does it make sense? The length and angle, they're all in scale by having a reference there. Okay. And the second graph is about 3 different components. As I said, we have up to 9 components. Right? We have up to 9 components. Therefore, I'm selecting 3 of them to plot into the same graph. Well, I might pick more or less in the exam to do the same thing, right? Because once again, we have up to 9. So first, phase A0 sequence. Phase A0 sequence, you need to be clear. Who is it, right? Who is it? VA0, right? You obviously need to be clear. Who are they, right? VA0, okay. Phase B positive sequence, okay. VB plus. Phase C negative sequence, VC minus. How to plot this? VA0 is part of the what? Symmetrical component. Does it make sense? It's the easiest one. Very nice. It's the easiest one. Nothing but this guy. 0.6, 90 degree. Okay. Then in the exam, obviously, you want to first of all find it, right? First of all, you need to find it. Find the correct phaser, and then we talk about how to plot, right? This is what you need to do in the exam. Next, positive sequence of the phase B. Positive sequence of phase B. How to find the positive sequence of phase B? What's the easiest way? Anyone? Any idea? How to find a VB plus? Multiplied by 1/3? No, that's not what we learned, Eamon.
Would it be VA plus times A2 or A squared?
That's the easiest way. I agree. Gavin is right. Okay. In other words, you're looking for VB plus based on whom? VA plus. Based on VA plus. VA plus, VB plus, and the VC plus, they are in the same sequence, right? They are balanced. So if you know VA plus, it's very easy to find VB plus. Once again, because they're balanced, right? In other words, if you plot VA plus, VB plus, VA plus is here, right? Where's a VB plus in this phasor diagram? Where is it? VB plus here, VC plus here. Does it make sense? Because positive sequence. So what happened actually? So if you know VA plus, which is part of the symmetrical components given, you keep the same magnitude and reduce the phase angle by 120 degree. You are reaching the VB plus. Does this make sense? So VA plus is whom? VA plus is 130 degree, right? 130 degree. So VB plus is what? Magnitude of 1 as well. Phase angle of what? Minus 120, right? Minus 120. I mean, from 30 degree minus 120. So does it make sense? Negative 90 degree. Does it make some sense? This is the easiest way. Similarly, how to find the VC minors. VC minors, we still go to the VA minors. Okay? If you think of this definition, VA minors, VB minors, VC minors, they are once again, balanced. So you know VA minors, where's VC minors? VC minors is over here, keeping the same magnitude. However, you reduce the angle. I'm sorry, you reduce the angle by 120 degree. You are reaching the VC minor. Does it make sense? So VA minus is what? VA minus is this guy. VA minus is 0.8. Okay, negative 30 degree. You reduce that by another 120 degree. So 0.8, negative 150 degree. Does it make sense? These are the three components we are looking for this particular problem. Any questions? Does it make sense? All right, if this is okay, then go ahead. Once again, it's 1.8, 0.6. So we begin with one negative 90 degree here. Okay. Being clear, this is VB plus. And then VC minus, negative 150 degree. Negative 150 degree is how much? It's about here. Right? However, it's 0.8. Okay, so it cannot be that long. It's about here. VC minus. This is the negative 150 degree, which means this angle is what? 30 degree, right? So this is how you come up with these VC minors. And similarly, VA0 is 90 degree. It was 0.6. So take a look to see any questions. Does everything make sense? So once again, up to 9 components. Thank you, Anil. So up to 9 components, we might ask anyone or any some of them, right? So in the exam, well, you have plenty of options, or say I have plenty of options. Right?
How did you do the VA0 sequence?
VA0 sequence, VA0 sequence. VA0 is one of the symmetrical components. You need to first of all realize that.
Oh.
Does it make sense? Your zero sequence is symmetrical components containing the VA0. So containing so symmetrical components is about everything, every sequence components for phase A and phase A only. Okay, this is your understanding. Of course, if this problem is asking, let me ask you, we'll say phase C this time. For phase C, zero sequence components. What is it? VC0 equals what? How to find VC0?
So if it's VC0, we already have VC minus, right?
So?
Oh, we can't convert that, can we?
No, you can't. You can't. Very good. Very good mistake. I mean, it's very good to make that mistake. No, I mean, very good to make that mistake now. Right? So, instead of in the exam, obviously. So, or I keep thinking how to find VC0.
Isn't VC0 just VA0?
Excellent, excellent, excellent. Why is that? Again, those are the definition of sequence. Positive sequence, negative sequence. The zero sequence means what? They are same, right? They're exactly same identical phasor. Same magnitude, same phase angle. Therefore, they are unbalanced. Right. If you want, you plot this here. Identical with the VA0. That's why I just add a comma and VC0, saying this is representing both. Right.
So for VB plus, how we got negative 90, that's because we subtracted obviously 120.
Yes.
Is it the same as saying plus 240?
VA plus 240 degree. Yes.
Okay, so that's the same
Yes.
equivalent.
Yes.
Okay.
Yes. Yes. And then from the phasor diagram, if you plot that one, it should be same as well. Yep. Well, I can tell you now that in the exam, yes, I'm gonna ask for different components. Okay, I'm gonna ask for different components. Be ready for those. Be ready for those. Okay. Because if I'm giving you the three-phase unbalanced voltage and asking for the different components, well, you need to find the symmetrical components as well, right? Where you can tell anything. You can tell up to 9 components based on symmetrical component. Any questions?
And so since zero sequence is they're
Easiest
all
one.
equivalent to each other, correct?
Yes.
VA0 is going to equal VB0 and VC0.
Yes, easiest one. Yeah. Yeah, as long as the concept is clear and the easiest one. All right. One more example. How about that? One more example. This time let's do go back. Let's go back by even three-phase unbalanced voltages VAN, VBN, VCN, sorry that the number is a little bit tricky, but it's good exercise. Find and plot. First of all, the symmetrical components. Voltage symmetrical components. Second, the three-phase negative component. 3 is a negative sequence component. Phase B, zero sequence component. And phase C, positive sequence component. Well, of course, this time I'm going to make sure I'm not copying the wrong numbers here. But anyways, you guys have about 10 minutes from now on. Go ahead.
Dr. Zhao? Hello?
Here I receive a question from Sawyer. Is so the given the VAN is nothing but the VA we learned from our previous like the formula or equations. Okay, they're the same thing because the voltage symmetrical component is based on the phase voltage, not line voltage. So VAN obviously phase voltage. Okay, VAN is VA. Yes, VAN VA. Yes. Sure.
So if we're given VAB, VBC, we need to do the conversions to VAN, right? Because it's phase. Dr. Zhou?
I don't think he can hear us, John. So just write it out.
Are you talking, Kevin?
I was not, but Jonathan was.
Yeah, I can hear you now anyways. So go ahead.
If we're given VAB, should we convert that to VAN then to get the sequence or the symmetrical components?
Well, first of all, I'm not planning to do that to you. Okay, so there's a second in the balanced system, in balanced sequence, you can do that. In unbalanced, you cannot directly apply that root 3 phase angle 30 degree. You can't directly apply that.
Oh, so that's why we always assume when you're giving us the voltages that it has to be obviously for each phase of the load.
Except otherwise being told.
Oh, except unless it's completely balanced, right?
Yeah, and right. I mean, but once again, I'm not planning to do that to you. It's
Okay.
not necessary. It's not necessary. No, I see. I went to drink a little water. That's why I removed my earplug. I think by that time you guys are talking. That's why. But it's okay. Now I have my earplugs on all the time. So I'm presenting the calculation result for symmetrical component, and Any questions regarding these results? And then what matter is the graph, right? The graph. First, you're plotting the symmetrical components, nothing but these three guys. Easiest one. So 0 degree, 90 degree setup. And the longest one is 90 with the magnitude of 390. 24 degree. It's not very easy to be accurate, but we try our best. Okay, this is the VA plus. This is the VA plus. Second one. Okay. -24. Next, I think the first one is becoming easier. The first one's magnitude is basically what? 1/3, right? 1/3 of the VA plus. 1/3 of VA plus magnitude. Well, this height. And it's 80 degree. You need to keep a little bit gap between the vertical first, right? Third one is 230. 230 is what? It's basically a little bit less than the double of the first one, VA0, in terms of length, right? And it's positive 34 degree. 34 degree is about here. Then it's just like this. VA minus. Any questions? You guys can hear me, right? Can you?
Yeah.
What a relief. Sometimes I feel like scared, very scared. Second one. Any questions regarding the first one, symmetrical component? Once again, no way to be accurate. Okay, this is hand sketching the angle. How could be accurate? No, I'm not demanding that. But they must in scale. It must make sense. Okay, must make sense. If it doesn't make sense, then you're gonna lose points. Okay. Second one, read carefully. The problem asking for three-phase negative sequence components. Three-phase negative sequence components. Who are they? Once again, you got to understand who are the ones the problem is asking for. Who are they? VA minors, VB minors, and VC minors. Three-phase negative sequence component. No more, no less. Okay, no more, no less. Remember this in the exam. I'm asking 3, give me that 3 exactly. No more, no less. Okay. You list all of the 9 components over there. Guess what? You got a 0. Okay? It's clearly indicating you don't understand what I'm talking about. Did I make myself clear? Right. Thank you. All right. So let's see. VA minors, VB minors, and VC minors. So first of all, VA minors is given. Okay. VA minors, this guy is not given. It's already obtained. We already have it. And also notice this is same sequence, so balanced. Okay, this is negative sequence, balanced sequence. So same magnitude. So same magnitude. So we got this guy over here. VA minus, VA minus. Okay, this guy here. And we know this angle is basically 34 degree, right? Then how to plot VA, VB minus and VC minus? Well, we don't need to do real calculation actually, right? VA minus to VB minus is doing what? Same length, same vector length. However, what? Increase your degree by 120 degree, right? So 34 plus 120 degree. That's the phase angle of VB minus. Does this make sense? So it's 154, 154, 154. 154, well, not easy to sketch either. However, I'm not that demanding. Okay, not that demanding, right? Does it make sense? VB minus. The still balance VC minus is what? VC minus has also the same magnitude. However, you decrease the phase angle from VA minus by 120 degree. Then what do you got? Close to negative 90 degree, but not exactly, right? Be very careful on this, right? Be very careful on this. Is equals to what? 80 something, 86 degree, right? Negative 86 degree. So be very careful. You can't perfectly align with the vertical line, okay? It's very close, but not exactly. VC minus. Does it make sense? You pretty much rotate from phase A sequence component, right? You rotate plus 120 degree or minus 120 degree, or depending on which sequence it is. Any questions?
So just to make sure, with this negative sequence, if they have a 120 degrees difference between each individual one, and the same magnitude, that would be considered a balanced load, right?
Yes, yes.
So basically, the closer in the
not balanced load. No, I'm not talking about balanced load. I'm only talking about the sequence. This particular sequence they're balanced.
Well, if the VB, VA, and VC minus, if those magnitudes are getting closer and closer to equal, and the degree is each of them are around a 120 degree, that's when we would be able to use for power. That's when we'd be able to use the three-phase balanced equation, right?
Correct.
So if we seen that we were close to our three-phase sequence and we wanted to just be quick with a calculation, we could get a reasonable approximation by just using the three-phase balance power.
Well, that depends. That depends. You need to bring up a specific example showing how you approximate that, and we can judge. How close is it? Maybe close, maybe not. However, that's not very safe. In a power analysis, in a real accurate power analysis, you have to spread your picture into three sequences and analyze them individually. That's the safest way to analyze the power system.
I say that because we're never going to be exactly precise usually when we're measuring. So what's the measurement value? Like, is it within a degree of each other and a magnitude of a few percentage points that they'll consider it balanced? Because if you're trying to measure each individual phase and the magnitude wouldn't, it's not like you would get them exactly. Theoretically, they should be the same, but what do they typically say in industry is considered three-phase balance? Like, what's the...
Oh, you're saying in the real application, you're not able to measure the phase voltage. You can only measure the line voltage. Is that what you're saying?
Yeah.
Because you only have the phase voltage, so you only have the line voltage. However, you can't do the easy conversion to find the phase voltage. Therefore, you can't find the symmetrical components either. That's what you're saying, right?
Oh, okay, yeah, that's true.
But so if that is the case, then well, there's one solution. When I do this experiment many years ago, I can create a neutral point by using very huge resistance. Okay, so 3 lines you have, right? Yes. Technically, you can only measure the face to face, or say line to line voltage, here to here, here to here, and here to here. But there's no neutral point for you to access. You can't find the phase voltage, right? So what I did is like this. I do a big resistance, also balanced, these 3 balanced, create a neutral point here. And then I measure from here to here as the phase voltage. This is what I did.
Okay, that's a pretty cool idea.
Yeah, and that's actually also practical. I learned this from my advisor. I wasn't that smart. Create this. No, I was taught. Okay, I just learned. But here, to your approximation, because my expertise is not power analysis, actually. However, generally speaking, people calculating the real power only using the positive sequence. Negative sequence and zero sequence, they generally speaking very small. And we extract those out and then use only positive sequence components to calculate the power in the system.
So if we don't really have, per se, access to those neutral points, like let's say consumers and their electrical generators, would that be the process that they're going to try to do, is get as close as they can to the motor phase leads and short some neutral point together? Is that how they would be able to measure?
You mean, well, they are the generator, right? So the voltage they're generating is reference.
And what happens if, say, the motor is a delta wound? Would they still then short to make a neutral point?
First of all, why you have to have a neutral point for at the generator side?
Well, I thought we were supposed to get the phase.
For
So, like, let's say the motor is not wound correctly, and you have a delta wound motor, and you want to know what the VA in this case is to get the symmetrical components to see maybe if it's balanced or not. So, what happens if their generator that they're using at the factory isn't, let's say, 3-phase neutral or a Y connected source? What if it's a delta connected source? Well, what then would they do to get access to the neutral point?
if it is delta connected, well, they don't have a neutral point. They to be honest, in the generator system, I barely see delta connected the generator.
Okay. Okay.
All right, let's go here further and the third one is asking for the phase A negative sequence component. Phase A negative sequence is available here, as well as here. Phase A is the easiest. As long as you have symmetrical components, you already have it. But before that, VA minus equals to, you need to write them down. You need to write them down. The reason for writing them down is for you to understand how big they are. Second one, phase B0 sequence. Phase B0 sequence is who? Same as phase A0 sequence. Same. Zero sequence. Phase C, what is it? Phase positive sequence, okay. Phase C positive sequence. No, we don't have it yet. We don't have it yet, but it's okay. We derive from VA plus, right? We derive it from VA plus. Where plus is over here. So in positive sequence, VC plus is equals to the same magnitude. However, phase angle, you need to do what? The positive sequence. Plus 120 degree, right? Does it make sense? 90, 20, 20. Does it make sense? Any questions regarding these three vectors? Obviously, you need to first of all come up with Huade. Right? This is the result, and if you plot them into the graph, once again, 390 is here, the longest one, a little bit over the vertical line, vertical reference line. So this is VC plus. Next, the VB0 at 1/3 length of it. 1/3 is about here. 80 degree. VB0, right? VA minus 34 degree. It's about here. VA minus. Here we go. Does it make sense? Any questions regarding this problem?
Where did we get VB0?
VB0 is equals to VA0. Remember zero sequence?
Okay, gotcha.
Yep. So once again, as long as you have symmetrical component, you know anyone else among those 9 I just mentioned, right? 3 by 3, 9 components. Any questions? Anyone can confirm my answer here? Anyone got the exactly same answers as I do here? All right, thank you, Anu. Anyone else? Good, Alex. Good.
Could you run over plotting the negative sequence one more time?
This guy, okay, here.
Yeah.
So first of all, is like by reading the problem, first of all, you need to understand what I'm asking for, right? So first, 3-phase negative sequence components, you understand, okay, I'm asking for VA minors, VB minors, and VC minors, right? And VA minors is the easiest one, and always the first one to go with. VA minors, you got it from the symmetrical component. Okay. So VA is here. So you can plot it into the graph first, okay, with certain lengths. It doesn't matter anymore because this is negative sequence in which 3 components are balanced, right? Same magnitude, 120 degree phase shift. So you, after plotting the VA minors, which has 34 degree of phase angle, you know, negative sequence is like this, right? We just did it here. We just did it here. This is negative sequence, right? So VA minors if is here, and then we are looking for whom? Okay, VB minor is gonna be what? Increase the phase angle by 120 degree. VC minor is just decrease the phase angle by 120 degree, right? So go back to here. So VA minors now it's here. Increase 120 degree will reach VB minors. Decrease 120 degree will reach VC minors. So same length. Okay, that's easy. So 34 plus 120 degrees, 154 30. That's why this is 154 degree, right? And then 34 minus 120 degree here will end up with is as like negative 86, right? Negative 86. So this angle is negative 86. 34 minus 120.
Okay.
Of course, I'm not counting in the digits. Maybe you should in the exam. However, the reason I'm not counting in is, anyways, we're plotting a what is approximated angle. So point 37 degrees is nothing comparing to our error, right? So, yep. Yeah, this is how we get there. Okay.
Thank you.
Sure, no problem, no problem. Any other questions? All right, if this is fine, then now let's jump into the review of the midterm one. Review of midterm one. I'm not ready for the problem, but let me basically talk about what problem gonna be there. Okay, what problem gonna be there? First problem. You're gonna have 4 calculation problem this time. Okay, 341. Midterm 1. Problem 1. Quiz 1. Problem 1. Do you understand what I mean? Well, not exactly the same as the quiz 1, problem 1. That's impossible. Don't even think about that, of course. What I'm saying is the problem 1 is just a single phase power calculation. The closest the problem or example, you can go to the notes example and also the quiz 1, problem 1. Asking the power there, asking the power there, here, there. And maybe also the power factor correction. Okay, this is problem 1. Problem 2 is three-phase power calculation problem. You need to go to the notes. We have one example including everything. Be careful. Answer exactly what is asked. What I'm saying is, because it won't be surprised that if you can have the table established, right? You might I'm ask for the phase voltage, line voltage, phase current, line current. Right? I might ask any one of these, right? Up to 8. And correspondingly, you can use line or line to power or phase to phase to find the power, right? However, I might just ask for 1 or 2 or 3 out of these 8. You're not giving me anything else. Okay, you're giving me something else. You're violating this word exactly. Therefore, you're gonna lose point. Okay. And if you list all of these answers over there, you got a 0. Okay, don't list this thing over there. Don't present everything. I'm not asking for everything. Okay, remember this. Remember this. Okay, the notes example is the best one to learn, to follow. Okay. And also, I'm not planning to ask for the power factor correction for this problem. I don't think so. Yeah. This is problem 2. Problem 3 is per unit system. Per unit system, which you need to wait next lecture to have a couple of examples. Okay, by then we're gonna discuss more about the per unit system. Okay, by next Monday. Next Monday.
The homework, which has a couple of per unit system problems on it,
Okay.
is due tomorrow.
And
I just didn't know if we were going to go over some examples before, so we'd have an idea of how to answer the homework problems.
okay, let me. That's a good point. I thought I gonna have some time today, but how about you guys try to do some, and I won't well, anyways, it won't be counted. You guys can try something by yourself, do something, and homework. And by next lecture, let me present the detailed solution for these 2 examples as well as the homework problem. How about that?
Okay.
I mean, due to the time, we can only do this, right? I mean, the rest of the time, well, I don't think we have time to really do the examples. We have to wait until next lecture to have the per unit examples.
The only difference with those per unit stuff is just
Difference between
per unit, right?
Between what? The difference between what?
Like our regular calculations per unit stuff isn't it just like they'll give you impedance in per units and then you just have to find it based off the base they give you?
And the real example I'm gonna give you is actually how to change those the base. 10 ohm is the actual value, right? 10 ohm at one system 1 might be 0.8 per unit, but in the same 10 ohm in system 2 might equal to 0.6 per unit. It's different. So my example is mainly try to help students understand how to transfer this. Yeah, from system 1 is 0.5 per unit. In system 2, what 10 ohm is in terms of the per unit. This is the examples.
We didn't have a problem like that on the homework, right?
Not quite same, but essentially they're same.
I don't think
I thought there should be 2.
What is it?
they didn't have different systems though. They all used the same base.
Well, then probably not exactly same. Then my example is probably a little bit deeper. Also, by the way, have you guys ever think what does it mean by 2 different systems? Have you ever think practically what scenario you have 2 different systems? You have to consider the same quantity in 2 different systems. What does it mean?
Right.
Visualize it into real application. What we are talking about. Have you guys ever think about that? Anyone knows? Anyone know why? In what scenario was it? Excellent. I received the correct answer from Anil. It's about transformer. Okay, in the power system, different voltage level networks is connected, hooked up through what? Transformer, right? So primary end, there's one system. Secondary end is another system. You have the same quantity, it's the same actual value current or whatever it is. In the primary side is 1 per unit. The secondary side, it becomes 0.5 per unit. That's why we need to learn how to transfer this. Not necessarily very, very difficult. However, you need to understand the concept. Is it good for that? Or you understand it's a little bit delayed, but
It's good.
yeah, it's have to do so. Can only do this time. All right, let's move on to problem 4. Problem 4 is symmetrical components. There's no surprise. Symmetrical components. Well, example 2 and 3 of today's lecture. Today is 9 in notes. Okay. Always try to follow the notes examples rather than anything else. Okay, this is my suggestion to you guys. Is this clear? Any questions regarding the midterm one? In terms of time, be careful. Be careful that the time of the midterm one is what? Anyone knows? Maybe you can't remember it exactly. However, just to remember one thing about the time, okay? It's earlier than our lecture time upon the request from many of you. Is that clear? It's earlier than our lecture time. Well, our lecture time begins at 4. However, because this time length of the exam is long, so it begins at what? 3:35. Okay, 3:35 is the time for starting of the exam. Yeah, I see the answer from two's answer is closest. 3:30. No, not exactly. 3:35. Okay, 3:35. Noah said 15 minutes earlier. No, it's actually what, 25 minutes earlier. 25 minutes earlier, right? And of course, I have one student's request and a different time slots, which has been assigned. Okay, and these are all based on the exam time survey result. If you reported that you have trouble of attending that time slots, accommodation has been arranged. All right, this is about exam, and now let's talk a little bit about the quiz. This is a quiz. Also, very good example for preparing the midterm 1, problem 1. Okay. And I want to say some small things here. First, this problem 1 here, I saw too many students. Just too many students are doing this. Look at this inductance. 254.65 millihenry, right? I see too many students writing like this. Is it okay writing like this? you're not losing point this time. However, this is absolutely not okay. Okay. You see here, the inductance is given like this. How could you have L again? This is Z sub L is the impedance of the inductance rather than inductance itself. You can't write L equals to this. Obviously, it makes no sense. You can't L equals like this and also equals like this, which is different. It doesn't make any sense, no matter how you think about it. In terms of the concept, this is the inductance. This is impedance. Okay, inductance is not equals to impedance. You can't do that. Here I have a question from John. No multiple choice for the exam. No, not this time. Midterm 1 has no multiple choice. Is that good news?
Sure.
Yeah, maybe. Yeah, maybe. Yeah, I like Eamon's answer. And 2, what do you mean by complicate? I'm not sure what that word means. 2, what do you mean by complicated? Is that complicated? No, this is not complicated. Okay. You have to do this. Impedance is impedance. Inductance is inductance. This is electrical engineer must understand this. The difference between this. It's not something we can kind of whatever like that. No. And what does it mean by P is missing? Anil, what do you mean by that? Yeah, you know why we don't have enough time? Because you guys don't speak. Okay. Right. Anyways, this is one thing about the quiz, and another thing I want to talk about is the power. The power. Remember to label lagging or leading, otherwise you're gonna lose point. Okay. I mean the power factor is lagging or leading. It's absolutely matter. Absolutely matter. Okay. Another thing is in my grading, I'm using this plus a cross plus a check. What does this mean? You guys understand what I mean here? Of course, 3 types, right? Cross means wrong, check means right. And then what does this mean?
Partial credit.
Partial credit. Yeah, basically, yes, basically right. That's I think is a very nice in between. Yeah, in between is fair answer too. That's right. Kind of right. No, there's no kind of right. Either right or wrong. Kind of right. No, I don't like that word. I don't like that word. The key is this. This guy, you receive point. The credit is given. Receive point. This is what? Lose point, of course. How about this guy? You're not losing point, okay? You're not losing point either.
Isn't that if we
Not
do
losing
like
point
one
means
step off,
it's
we get
receiving
pressed,
point.
right?
Okay. The receiving point this for this case. However, why you have a cross here? It means this result is wrong. However, the reason is because of the previous mistake, like this. So at this step, you are not doing anything wrong. However, the result is definitely wrong because your previous step was wrong. The previous result was wrong. This is how you understand this. I'm using 3 different marks to indicating different comments, pretty much. Okay, so correctly interpret my labeling here. Okay, your receiving points here, partial credit, therefore, is a good and accurate enough interpretation. Okay. And the next thing I want to talk about is oh yeah, the problem two here. The problem two here. We just when we answer for this kind of problem.
We lost audio.
How about now?
All good.
This is so what I'm saying, where are we at? You have to tell me that.
Just when you switch screens over.
Okay. A screen over here. Okay. So you just need to give the answer like this. Okay. In other words, you don't have to give a phase A, phase voltage, phase B, phase voltage, phase C, phase voltage of Y. No, you don't have to do this. You don't have to do this. I appreciate it, but you don't need to do this. Everything is actually out of the per phase circuit, so give the result. One result is fine. You don't have to point it out which phase. And you don't need to present three phase either. And also, yeah, I have another thing here. Look at this. What you are seeing here is the file size of your submitted quiz. The quiz that just contains the answers for two problems. However, I saw one student's file is as large as almost 10,000, which means 10 mega. This is too big. This is really too big. So you want to really check your file size, okay? Too big size is not easy to upload, and is actually also not easy to grade. And not only that. Hold on 1 second. Oh, not this one. I mean this one. 64. Oh no, not this one. I think this one as well. This is too big. This is even bigger. 64. This one is the zip log file. It's not anyone's uploaded file, but this one is. It's too big. This one is too big. To be honest, I think even this 4 mega is a little bit too big in my opinion. I mean, when I grade my problem is when I grade is like this. When I say I give a comment like a very good. I finished typing. However, it takes 2 seconds to show up. Good question. How you guys avoid too big size the file? Many of you can do that. I mean, I think different software and different export different file format matters. You can do a little bit of exercise, and since everyone has no trouble of uploading file, I think it's still fine if you end up with 9 mega. Yeah, you can lower down your quality a little bit. Okay, you can try to do that. How about try it, and then you send an email to yourself to see if you can have if you can read it. That's the bottom line, right? You don't want to send me a very small file, however size is small, however it can't read it. Then that's bad. That's bad. Office Lens app to turn pictures straight into a PDF. well, it's you probably, because the software I use is this guy. I can show my screen. And I'm using this one. What's new? Nothing new. This guy, CS. Cam scanner, right? So how many of you guys are using the same thing? Okay, so do this as possible as you could. Okay, if you can't, well, I will take it. Okay. I mean, the bottom line is, as I said, if you have no trouble of uploading your file, it'll still be okay.
Would you also take a JPEG or no?
JPEG, no. Picture, no. I can't take it. It has to be PDF. This is solid requirement. Very solid. How about that? This is of course minor thing compared to the other issues, but well, just a try. Try some. This file size actually matters somewhat. Any other questions, concerns? All right, thank you. All right, thank you all for attending today's lecture, and talk to you guys next Monday. No problem, Gavin. All right, bye now. Thank you, guys. Thank you.